Okay, let's consider this. In this case, I have two parallel plates that are, one is charged positively and one is charged negatively. They are a certain distance, d apart. If the separation between the plates is small, then the electrical field is going to have the same expression as the expression for an infinite plate. Remember, for an infinite plate, when we have just one plate, the electrical field is given by sigma over 2 epsilon 0. So the electrical field due to the positive one that's on top is going to be like this, given by sigma over 2 epsilon 0. And then the electrical field due to the negative one at the bottom is going to be given by the same expression and is going to point in the same way. Remember, electrical field points towards negative and away from positive. So in here we have sigma over 2 epsilon 0 plus sigma over 2 epsilon 0. That's why it is sigma over epsilon 0. That's the overall electrical field due to both plates. And it's going to be constant throughout that surface between the plates. The electrical field outside is going to be 0 because the electrical field due to the positive is going to be like this, and the electrical field due to the negative is going to be like this. They are the same magnitude but opposite directions, so they cancel. This particular situation, if we set up our electrical potential here at 0, then since I have a constant electrical field, E dot ds gives us minus Ed. So my change in potential, or VB minus VA, is just minus Ed. It depends on the electrical field and it has a linear relationship on D. Now, this situation, whenever we have two parallel plates to each other like that, with one charged positively and one charged negatively, that's what we call a capacitor, which is a device for storing an electrical charge for a short amount of time. The definition is like what we just saw. A capacitor is whenever we have two conductors separated by a small distance, whether they are two parallel metal plates like the one we discussed a second ago, or two concentric spheres, or two concentric cylinders, etc. And these two conductors, they have to carry opposite charges. One has to be negative, the other is positive, such that the net charge is 0. It's equal charges, but opposite, so the net charge, the sum of both, is 0. Now, we call them capacitors because of their capacity of storing charge. That's the key, store an electrical charge. So we measure their capability of storing charge by what we call capacitance. And capacitance is defined as charge over voltage, charge per unit volts. Its unit is what we call the farad, so it is coulombs over volts. Capacitance is always a positive quantity. So actually here it is this, the absolute value. Okay, we'll see in a little bit in another video that the capacitance for a particular capacitor is constant and determined only by the geometry of the capacitor. Now, farad is a very large unit. Normally, capacitors are going to be in the picofarads, sometimes in the microfarads, usually not more than that. Example capacitors, this is like the early capacitor, that what we call a Leyden jar. So in this particular case, we have like a metal surrounding, like this metal here. surrounding this glass bottle. The metal, like in this case, is connected to a positive charge, and then you have like a chain going down in the middle here. We don't see it in this case really well, but that chain is going to carry the negative charge. So negative, positive, that's the early capacitor. That's when people start talking of capacitors. And then here is another version. This is very similar to the one you used in lab, parallel plate capacitors. So these are two plates that are circular. Each one of them has an area A, and you kind of make your electrical connections here and you charge them up that way.